All right, in this tutorial we're going to pick up where we left off on a discussion of momentum. We are going to try to tie momentum with a new way of looking at force and the second law of motion. This is what Newton originally did. It is the more general form of expressing the second law of motion, whereas the one we introduced, F equals ma, is limited to certain cases. It worked for the case we worked at when we did that unit, but now we're going to look at like I said, a more general way. So let's start with what the second law of motion is. A net force we know is equivalent to mass times acceleration. Okay, and in the problem we saw above with Biff jumping on the scale, we saw that we weren't given acceleration, but we could tweak it by its definition and relate it ultimately to a change of momentum. Okay, so a reminder of something we learned a long time ago. This equation assumes that mass remains constant during the interaction. And if this is not true, then we can't use F equals ma. We have to use a more general form. Okay, so that's what we're going to do right here. So we got F equals ma, but by definition, A is delta V over T. Okay, so we can restate the second law very simply as F equals m delta V over T. And if you look at the numerator, we should recognize that from what we learned prior is that that's just delta P over T. So we have a new way of writing net force. The net force acting on an object is delta P over T, which is, I'm going to put delta there, you don't have to, but that's the rate of change of momentum. Okay, so the rate, that's what the delta T is telling us, how quickly momentum is changing. That has a pretty profound way of looking at force at all levels for all situations. It doesn't sound like much. It might just sound like we're just changing the words around and looking at a different way, but it's actually more useful and superior to looking at F equals ma for reasons we'll see right now. So we can now deal with the case when the mass of the object is changing. And we're going to deal with the simplest case where it's changing at a constant rate. All right, so the classic example is a rocket. So a rocket takes off and it starts ejecting mass out of its bottom, and it does it usually at a constant rate. So if we know something about the rate at which it's changing mass, we can understand how much force it is exerting in that case. Okay, so let's look at a new example. We're going to introduce a new concept called mass flow rate, but it shouldn't be too hard. All right, so let's say at the moment of takeoff, a rocket expels propelling gases at a rate of 1,200 kilograms per second. So that's brand new to us. We've never seen something as kilograms per second with a speed of 50,000 meters per second. So the rocket's expelling gases at a very high speed and at a rate of 1,200 kilograms per second. We can ask what force is exerted on a rocket because that's going to determine how quickly it takes off. So what is this 1,200 kilograms per second? Well, the units kind of give it away. It's units of kilograms or units of mass divided by time, so it's called a mass flow rate. So there's another rate we're introducing. Okay, and mass flow rate we're going to give the symbol m dot. Okay, the dot comes from a calculus thing. We'll just use it as a way of saying rate, and that's by definition the change in mass over time. So how quickly you're losing mass, or in certain cases, how quickly you're gaining mass. So even though this has two parts, think of it as one quantity. And in the problem above, the 50 meters per second is simply the velocity of the gases. Okay, so how do we put this together to find the force? Well, if we go back up to this equation, we say F equals the rate of change of momentum. Well, what does that mean? Okay, so I'm going to go back up to our equation box. So there's two ways you can look at delta P over T. Okay, at least in a simple non-calculus form. You can look at that as your mass staying constant, and the delta P is coming from the change in velocity. So it can be looked at as like that. That's ma. Or you could look at that as mass changing with time at a constant velocity. So note algebraically, we've got delta mv here, whereas here we got m delta v. Both are ways of changing momentum. So in the very beginning, when we introduced the second law, we were always talking about velocity changing with time. Here we have a problem where mass is changing with time, but we can use the general form of delta P over T to help us figure out force. So going back to our problem, if this is the equation we want, let's break that up into delta M over T times V. Okay, because delta M over T is our mass flow rate that was given as 1,200 kilograms per second, multiplied by how fast the exhaust is coming out, 50,000 meters per second, and you multiply that and you get a very large number, 6 times 10 to the 7th. And kilograms per second times meters per second is kilogram meters per second squared. In other words, it's a Newton. Okay, so look at that problem carefully. Look at all the little details there, especially this idea of mass flow rate. Make sure if you have any, or you understand. If you don't, come in with questions. All right, so I'd like you to try this on your own. Okay, we have water leaves a hose with a speed of 20 meters per second at a rate of 1.5 kilograms per second. It hits the side of a car and comes to a stop. Okay, let's assume no splashback. What force did the car impart on the stream of water? Okay, so in order to stop the water, the car's side had a part of force. All right, we're not given any acceleration, we're not given any mass. Instead, we're giving two pieces of information that might not seem like they're relevant, right? This is how fast the water's coming in, and this is how fast it's coming out of the hose. That's m dot, because of the kilograms per second. Okay, so it's very similar to the other problem. We can say F is delta P over T, and in this case, it would be how fast the water is moving as it hits and the rate at which the mass is changing in a sense. Okay, it's coming out of the hose at that quickly, so when we bring it to a stop, that's giving us an idea of how much mass is hitting the car at any given time interval. So that when you understand it like that, then the numbers are obviously pretty easy. 20 times 1.5, I'm not going to put the units in, and that's going to equal 30 newtons of force. And then we could ask, how much water was used in 30 seconds of this? Okay, so let's say we're aiming the hose at the car for 30 seconds of time. As the hose or water impacts the car, it's feeling a constant 30 newtons of force. We can ask how much water do we use. So here we want how much water is simply mass. We got m dot, we got v, and we're given time here. Okay, so looking at our equations, this isn't a force problem. It's really has to do with the definition of m dot. So if m dot by definition is the rate of change of mass, then what we're looking for, the amount of mass that came out in a time, is simply m dot times t. So that was 1.5 kilograms per second times 30 seconds, and that tells us 45 kilograms of water was released by the hose in that time. And as it was striking the car, based on the rate of change of momentum of the water, it was feeling 30 newtons that entire time. Okay, so that concludes our introduction to momentum.